We've spent a lot of time talking about octahedral complexes, where we have six ligands coordinating a metal ion. But they don't all do this. We showed you a lot of different structures. And while this class is going to focus on octahedral complexes, because we're just introducing this, I do want to point out that we have a lot of different crystal field splitting patterns. We have just as many crystal field splitting patterns as we do geometries. And I want to walk through what some of those look like. So here is a tetrahedral complex, and the ligands are these circles here in the corner. I'm going to highlight them blue to make them pop out. And we're trying to compare these to the XYZ plane that we'll see our um, d orbitals align along. And so I have all of our orbitals here lined out and pointing along. And you'll notice it's really different than our octahedral complex. In fact, when we look at it, it's basically the opposite, because now our dz squared and dx squared minus y squared, which previously had lined up perfectly with the ligands of the octahedral compound, are now right in between the tetrahedral ones. There's no direct alignment whatsoever. And so these ones now are going to be lower in energy. Whereas our dxy, our dyz, and our dxz, these ones now actually point towards our compound. So we can see a lot of overlap here in the dyz. In the dxz, we see a little bit less, but it's these top ones here. And in the dyxy, it's kind of evenly between these, but these ones in the back and the front here are lining up really well. Um, and so as this tetrahedral complex, these ones that were the lower energy in our octahedral, these ones are actually going to be our higher energy. And when we see these crystal field energies, or the crystal field split, as those electrons and the ligands repel the d orbital electrons, we're going to see a split that puts those dxyz ones at a lower energy, dz squared and dx squared minus y squared at a lower energy, and our dxy, dxz, and dyz at the higher energy. And so we're going to have 3 of our d orbitals at a higher energy and 2 at a lower energy in our tetrahedral geometry. Well, now that we have a different pattern for that crystal field splitting, everything else is basically the same. Like, we're still going to populate these electrons as either high or low spin, depending on the size of that crystal field splitting energy, which will depend on the ligand field strength of the ligands that are coordinating to the compound. And it'll depend quite a bit also on the charge of the ion. Um, And some of the other ones that we've talked about quite a bit that are a little bit simpler are our square planar arrangement and also our linear arrangement. And so thinking about these ones, we can think for the square planar complex, and we're in the x and z, y and z, sorry, the x and y plane for our ligands right here. These are going to line up perfectly with things like the dx squared minus y squared. They'll be lined right along it. So those orbitals are right along those same axes right there. Our dxy is going to be right in between these two, but in the same plane. And so we're going to see less overlap, but still a significant amount, especially when we compare it to orbitals that are going to come up into the x plane and come out of that plane where our ligands are and have even less. And so our dz squared then also has that kind of ring of electron density in the middle, when and then density that goes along the z-axis. And so just based on which of our orbitals our ligands most overlap with or run up or butt heads with, those are going to increase the energy, and it won't be the same for each orbital for every geometry. And so here for our square planar complex, we see that we only have 2 of our orbitals that are at the same energy level. And then our dz squared is a little higher, our dxy is a little higher, and our dx squared minus y squared is the highest and significantly higher than the rest. And so when you're thinking about this, there isn't this one crystal field splitting energy anymore, right? We can see transitions here, 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 in between here. And so it becomes a lot more complicated to think through the wavelengths that will absorb it. And we tend to see more peaks in our UV-Vis spectrograms. Um, and so there's a lot more deconvoluting the data around complexes that don't fall into a nice, neat octahedral or tetrahedral arrangement, which is fine. It just makes it a little more interesting. And then for these linear arrangements too, this can go right along the z-squared plane. So it's going to line up perfectly with the d, or the dx squared, or sorry, the dz squared right here. And it's going to align really well with any of our orbitals that are just in this z plane at all, which is going to be our dyz and our dxz. And our dxy and our dx squared, sorry, dxy and our dx squared minus y squared are going to just be in this plane right here, the xy plane. And they're going to have the least amount of direct kind of repulsion from those ligands. And so we're going to get a pattern that looks like 2 on the bottom, followed by another 2 above it, with a more significant increase up to the dz squared. So in general, for these more complex splitting patterns, we'll see that most of them tend to be low spin complexes in general, and they fill from the bottom up, as we would expect for like our more degenerate ones. But they still take quite a bit of exploring as you create new compounds that are in these geometries. And here's a nice summary of the geometries we've talked about so far, and showing the different crystal field splitting energies relative to one another and the patterns that they make. And so the one we've spent the most time with, and that I'd like you to be the most familiar with, is our octahedral splitting pattern right here. I think it's important to know that our tetrahedral is the opposite, because we have a lot of our coordination compounds that have 4 ligands rather than 6 with them. I mean, like on a personal interest and research note, I think the trigonal bipyramidals are really fascinating as well, but that might be a personal preference. You can choose your favorite from any of these, but you'll notice that for each one, they're really different, and it's really just how those atoms are, or those ligands are arranged relative to our d orbitals.